Alright guys, so sorry again that I couldn't be here in person, but I am here with you in spirit and voice to give you this awesome lecture on types of chemical reactions. So here we go. So when we're talking about chemical reactions, basically there's two main ways to classify different types of chemical reactions. One, you can take a look at what the atoms actually do. Are they combining together to make something new? Are they breaking apart to make something new? Or are they simply just rearranging and changing their partners to make a new product? Or the second way to kind of classify chemical reactions is by what kinds of chemistry or phenomena take place. So is something dissolving, or is a precipitate forming from two liquids, meaning is there now some kind of solid that forms? Is it an acid-base reaction? Is there gas bubbles that are being evolved from it? Or is it like a redox reaction where you have the exchange of electrons, and we see that in a particular way as well? All right, so there's two kinds of ways that we classified. When you guys took regular chemistry, we were mostly talking about number one, by what the atoms do: combining, breaking apart, rearranging. Because you remember those were single replacement, double replacement, synthesis, and decomposition. Here in dual chem, we're going to talk about both kinds. We're going to talk about what the atoms do and the kind of chemistry that it takes part in some chemical reactions. All right, so before we talk about specific types of chemical reactions, first let's talk about aqueous solutions, because the most common chemical reactions, and most of the chemical reactions that are going to take place, especially in the lab and also in the real world, are when at least one of the substances is in an aqueous solution. So what is an aqueous solution? It's a homogeneous mixture of a substance with water. So basically it's whatever substance we're talking about mixed with water. So for example, sodium chloride, an aqueous solution of sodium chloride would have table salt, sodium chloride, dissolved in water. So let's take a moment to see what actually happens when substances are dissolved in water. So if you're looking at a ionic compound like sodium chloride, when ionic compounds dissolve in water, they dissociate into their ions. So sodium chloride is made out of a sodium ion with a positive charge and chlorine ion with a negative charge. And remember, that's because the sodium is going to give his valence electron to chlorine, and so he loses one, becomes a positive 1 charge. Chlorine gains one, becomes a negative 1 charge, and usually the positive and negative electrostatic force is going to hold them together, except in water. Okay, so in water, the H2O molecule also has positive and negative charges on in its molecule, and so they're going to tear basically the sodium and the chlorine from each other, and so that's what we call dissociation. So you can see, in this picture right here, the the oxygen of the water molecule is slightly negative, and so that's going to be tugging on the positive sodium ion, and the hydrogens of the water have a slightly positive charge, so they are going to tug on the chlorine ions, and eventually you're going to get the sodium ions, okay, that are pulled away from the chlorine ions, and they're all going to be basically surrounded by little water molecules. So that's what happens when you actually dissolve or ionic compounds. They dissociate. Now, not all ionic compounds are going to dissociate or dissolve in water. So salt definitely does. You put a teaspoon of salt in water, stir it up, bam, it disappears. But not all substances do. Sometimes you'll put a substance in water, stir it up, and it just kind of either floats there or it all sinks to the bottom. So the substances that completely dissociate into ions are what we call strong electrolytes. Okay, they can, and these guys can conduct electricity. Why? Well, remember, we've got charged particles, and anytime you have charged particles, you can conduct electricity, because electricity is basically just electrons jumping from one atom or ion to another. So solutions that contain free moving particles like these strong electrolytes, these substances that dissociate in water, are going to be able to conduct electricity. So if you stick a light bulb in there with some leads in it, the light bulb will definitely light up. Now, sodium chloride is a very strong electrolyte, but there's also weak electrolytes, meaning that they'll dissociate but not fully dissociate. So sodium chloride will dissociate, and all of the sodium is going to break apart from all of the chlorine ions. And so all of them will be free-floating in the liquid. However, there are some that are called weak electrolytes because not all of their ions are going to break apart. So these guys are going to basically have kind of stronger electrical forces that keep those molecules together and don't allow water to break them all apart. So they're going to have some free moving particles, but not as much as the strong electrolytes. And then finally, there are some substances, obviously, that we can dissolve in water, and they don't conduct electricity at all. And so this is going to be like sugar. Sugar dissolves in water, and the way it does that is by breaking intermolecular forces, not actually breaking apart ions, because remember, sugar is covalent, and they are held together by sharing electrons, not by transferring electrons and then having an electrostatic force hold them together. So when sugar breaks apart, their molecules are not charged, and so there are no charged molecules or charged particles floating around, and so they are not going to conduct electricity at all. So if you put a light bulb in sugar water, the light bulb will not conduct electricity at all. It will not light up. All right, so what if you have a compound that has a polyatomic ion in it, like sodium nitrate here, NaNO3? Well, when it dissolves in water and becomes an aqueous solution, the polyatomic ion is going to stay intact. Okay, so that's kind of key. Polyatomic ion stays intact. So what's going to break apart is the Na is going to break apart from the NO3 molecule. Okay, so sodium has a positive charge, NO3 has a -1 charge, and that's how it's going to split up. Positive charge of the Na, okay, the sodium, and then the NO3 clumps together and it still has its negative charge. All right, there are some ionic compounds, though, that do not dissolve in water. Basically, the electrostatic, one way we can think about it is the electrostatic force between these guys is so strong that it doesn't let water break it apart. And so silver chloride is an example of a substance that does not dissolve in water. So this obviously would be one that does not light up a light bulb. So we can see here in this illustration that high solubility, okay, is which we'll get to in just a second. Solubility means you can dissolve in water. So high solubility compounds are going to be able to break apart into their charged particles, and low solubility ones, you can see here, are just going to clump together and stay together in water. So usually they'll either float on top or just sink right to the bottom. All right, so I had mentioned it in the previous slide, and here it is officially. Solubility. Okay, that is basically our fancy word in chemistry for being able to dissolve in water. So a compound that is soluble is able to dissolve in water. And a compound that is insoluble, okay, note the prefix in, which means without, is not able to dissolve in water. Okay, so this guy would be soluble, and this guy here that clumps together still would be insoluble. So that's the two kind of vocabulary words that we use quite often when we're talking about being able to dissolve in water. Soluble means you can, insoluble means you cannot. All right, so we have come to the fun, because at this level we get to basically learn how we can tell if substances will be able to dissolve in water or not. And guess what? There is no easy way, but there is this handy dandy chart for solubility rules. And guess what? You do not need, let me rephrase, you do not need to memorize this. Okay, you will have this on tests and quizzes. You just need to know how to use it and remember to use it when you are working with some problems. Okay, so these are the solubility rules for ionic substances. So if you take a look, compounds, so the first part, obviously, these guys are able to dissolve. Okay, so these guys are dissolvable. All right, and so compounds containing alkali metals, all right, remember those are the ones in the first group on the periodic table, lithium, sodium, potassium, rubidium, cesium, right, and the ammonium ion. These guys are always soluble, so no matter what they're hooked up with, they are going to be soluble. Nitrates, bicarbonates, and chlorates are also soluble, so no matter what they're hooked up with, they are able to dissolve in water. Now the halides, okay, so those are the halogen group, group 7, okay. Chlorine, bromine, and iodine are generally soluble, except you see here we have some exceptions. So if chlorine, bromine, or iodine is hooked up with any of these three guys, they are insoluble. So the silver chloride that we saw earlier in the lecture, we said that was insoluble. Okay, so that's because this chlorine is hooked up with silver. There's also, it looks like, mercury and lead. Compounds that are with halogens are also insoluble. Sulfates are generally soluble except those that are hooked up with these metals. Okay, so silver, calcium, strontium, barium, mercury, and lead. All right, those guys would be insoluble. Now, if we take a look at the guys that are generally insoluble, so not dissolvable down here, bam. Carbonates are usually not soluble. Phosphates, chromates, and sulfides are usually not soluble except, again, we always have exceptions, except if they are hooked up with any of those alkali metal ions and ammonium. Okay, so basically if it's hooked up with these guys, all right, they're still soluble. But, you know, calcium carbonate, not soluble because calcium is in group 2 instead of group 1. Also, hydroxides are usually not soluble, except again if they're hooked up with alkali metals or the barium ion. Then they do become soluble. So like NaOH is soluble, okay, because Na is a alkali metal, all right, but calcium hydroxide is not soluble because he's in group 2 instead of group 1. So again, you do not need to memorize this table, you just need to know how to use it and need to know when to use it. All right, so here is some for us to try together. So we have to figure out if these guys are soluble or insoluble. So silver bromide. All right, so if we take a look at our solubility chart, bromine is a halide and he's usually soluble, except when he's hooked up with silver, mercury, or lead. And in this case, he is, hooked up with silver. So this guy is going to be insoluble. I'll put IS for insoluble. Calcium chloride. All right, so let's see. Chlorides, again, usually are, these they're part of the halides, and they are usually soluble, except if they're with silver, mercury, or lead. Well, calcium's not one of the insoluble exceptions, so this guy is soluble. Calcium chloride is soluble. All right, moving on to the next, we have lead nitrate. All right, so here on our things, nitrates, okay, are typically soluble, and we don't have any exceptions on this side. Fabulous. Okay, so that means that lead nitrate is soluble. All right, last but not least is lead sulfate, PbSO4. Okay, so sulfates are generally soluble, able to dissolve in water, but they do have exceptions. Silver, calcium, strontium, barium, mercury, and lead. Here we have it, lead. So this is an exception. So this guy is insoluble. insoluble. All right, so that's how you're going to want to make sure that you have this handy to figure out if something is soluble or insoluble. And you're going to see that it's going to come in handy when you guys are predicting products of single replacement and double replacement reactions. Woohoo! All right, so let's dig into the types of chemical reactions. And in this lecture, we're going to focus on classifying these chemical reactions via chemical phenomena that we see. So the first one we're going to talk about is the precipitation reaction. Precipitation reactions are a reaction that forms a solid, and the solid we call a precipitate when we mix two aqueous solutions. So over here on the right-hand side, we have a solution of potassium iodide and lead nitrate. Okay, and you can see both of those are clear, and when you mix them together, we get, bam, a precipitate. Okay, and so you can see that all of a sudden you get this dramatic yellow cloudy substance when you mix these two together. So this is what we call a precipitation reaction. Now, precipitation reactions do not always occur when you mix two substances together, obviously. So here, on the left-hand side is we're going to hook these two clear aqueous solutions together, and we still don't have anything in the middle. So precipitations do not always occur when you mix two liquids together, but when they do, it's pretty cool and it's pretty dramatic. Just a heads up, when precipitate is usually a cloudy substance. It's not going to be like, boom, big chunk or something that all of a sudden falls out of your solution and hits the bottom of your test tube or something. Okay, so precipitates are usually in the form of little particles, like little dust floating, or little like cloud of substance. And a lot of times they're just white, but sometimes they're kind of dramatic, like this guy here. All right, so your job, my friends, is going to be able to predict if a precipitation reaction will form. All right, because we're going to do a lab where you're going to see this, but you're not going to be able to mix these things all the time to verify if a precipitation reaction occurs. You're going to have to look at a chemical equation and predict the products and figure out, is a cloudy substance going to form. So what do we need? What tool do we need to use that? Well, we need to use that handy-dandy solubility chart that we were just talking about. Okay, so in order to predict if a precipitation reaction will form, we must know that only insoluble compounds form precipitates. And that makes sense because insoluble compounds cannot be dissolved in water. Therefore, you're going to see them still. Okay, so here is the reaction for what we just saw on the last slide. Potassium iodide and lead nitrate. Okay, and when that reaction takes place, this is going to be a double replacement reaction, meaning that they're going to basically trade partners. Ki is going to trade and become with NO3, and Pb is going to trade and be with iodine. Okay, and so what we get in the products is lead iodide and potassium nitrate. And so what we have to do is look at our solubility chart to see if either lead iodide or potassium nitrate is soluble. So let's take a look. Lead iodide. Iodide, okay, is part of those halides. They're generally soluble except when hooked up with lead. So that's why this guy has a little S by it, because that means that it's insoluble. Okay, so that means a solid is going to form, right? Because remember those, when we write out chemical reactions, we can either put G for gas, S for solid, AQ for aqueous, or L for liquid. That means pure liquid. All right, and so S means that you're going to have a solid form, and therefore that substance is insoluble. Now, if we look at potassium nitrate's characteristics, all right, nitrates are always soluble, and there are no exceptions. So this guy is still going to become aqueous. We're not going to be able to see the lead nitrate. It's going to be floating around as ions. It's going to be floating around as the K ions, okay, K plus ions, and NO3 minus ions. All right, so they're going to stay dissolved in water. All right, now sometimes we're going to mix two aqueous substances together. Okay, so two substances that are clear because the solids are able to dissolve. And what you get in the end is still a clear liquid. All right, so basically what that means is that the products of the would-be chemical reaction are both soluble. Okay, so meaning that they're both able to dissolve in water and stay as ions. And so when this happens, there's no reaction. There's no chemical reaction that actually takes place. So for example, potassium iodide and sodium chloride. All right, both of these guys, fall under compounds that are, contain alkali metal. All right, and they're halides, right, which are usually soluble, and it's none of the exceptions over here. So what that means is that there's going to be no visible reaction. What's going to happen is that the potassium iodide, okay, is going to dissociate, and you're going to have a bunch of K's and I's floating around in the water, and the sodium chloride is also going to dissociate, all right, and you're going to have a bunch of Na and Cl ions floating around, but they're never actually going to get together because the water is going to keep them apart. Okay, so no reaction occurs when both products are soluble. All right, so let's take a look at writing equations for precipitation reactions. Okay, so there's a couple steps we need to take when writing our equation for these. So we're going to write the formulas of the two compounds being mixed as reactants in a chemical reaction. Then we write the formulas of the potentially insoluble products that could form. Okay, so make sure that you write the correct, charge neutral formulas. So basically it means to crisscross. Remember, crisscross those charges, all right, to make sure that whatever chemical formula you end with is going to be a neutral substance. Okay, then you're not done there. Okay, so like in regular chemistry, we were done. We would just rearrange the reactants to make new products, crisscross, and done. You guys at this level are not done. What we need to do now is look at these solubility rules to determine whether these products are going to be insoluble or not. All right, if the potential products are soluble, you have to write no reaction, because remember, if both of the products that are made are going to be soluble or able to dissolve in water, they're never going to come together to make something that we can actually see. So you have to write no reaction for products that are both soluble. Now, if one or both of the products are insoluble, you need to write their formulas and indicate them as a solid, or S. Okay? And then, of course, last but not least, balance your equation. All right, so here is an example that we've got on this slide. Sodium carbonate and copper chloride come together. Okay, so we can see that we start out with two compounds. So they are going to reorganize themselves. They're going to switch partners in basically kind of like a double replacement reaction. And so sodium is now going to go with chlorine, and copper is going to trade places. All right, and his new partner is going to be carbonate. And so we've got copper carbonate and sodium chloride. Okay, well, if you look at the solubility rules, which I don't have up on screen right now, but if you looked back in your notes, you would see that carbonates are generally insoluble unless they're with the alkalis. Well, copper is not in the alkali metals. And so this guy is going to be soluble, so that's why we write the S. Now sodium chloride, all right, halides like chlorine are always insoluble except if they're with silver, mercury, and lead. And sodium is not one of them. In fact, remember the first solubility rule says that all alkali metals like sodium are always going to be soluble. So this guy is an AQ. Okay, and so we have one that stays dissolved in water, that's sodium chloride, and we have another substance that will actually hook up and find each other, and that is the copper carbonate, and so that's the S. So we will see a chemical reaction here. We will see cloudiness form in a precipitate form because copper carbonate is not soluble. All right, so here's an example. Write an equation for the precipitation reaction that occurs, if any. Because remember, sometimes precipitation reactions don't occur, and so that's what we actually need to find out. So write the equation when solutions of lithium nitrate and sodium sulfate are mixed. All right, and so we've got lithium nitrate here, and we've got sodium sulfate. Okay, so what we'll do is we recognize that, again, these are two compounds that we start with, so they're going to switch partners. Okay, lithium is going to drop the nitrate and go with the sulfate. Sodium is going to drop the sulfate, go with the nitrate. Okay, so our potential products are lithium sulfate and sodium nitrate. And so the next thing we have to do is look at our solubility chart. Okay, so lithium sulfate. So here we have sulfates, and lithium is an alkali metal. Those guys are both soluble. So that means that lithium sulfate is going to stay dissolved in water, AQ. That's what that tries to say, AQ. Okay, so we're not going to get a solid there. Now sodium nitrate, again, nitrates are soluble. There's no exceptions. And sodium is part of the alkali metals, and there's no exceptions there either. So this guy, again, is also AQ. So we're not going to have any solid products here. So we have to write no reaction. Okay. So this is going to be one of the keys in your pre-lab for tonight, for lab number 7, is that a bunch of the ones you're going to have to predict the products and then figure out if they're going to be soluble or not. If both of them are soluble, then you have to write no reaction. If you write anything else, if you hook up LiSO4 and Na3 on the other side, okay, and you basically that indicates that there's going to be a chemical reaction, you will get it wrong. Okay, so please make sure that you always check your solubility chart. You've also have one in the back of your lab manual. It's set up a little bit differently. It's actually kind of easier to use because you just look it up by the positive ion and the negative ion that's hooking up, and it'll either say S for soluble or I think, for insoluble, and there you go. It's super easy. Okay, so please keep this in mind when you're doing your pre-lab for tonight. All right, so let's do one more example before we do a couple of you-try-its. So write an equation for the precipitation reaction, if any, that occurs when solutions of lead to acetate and sodium sulfate are mixed. Okay, so the first thing we have to do is write the chemical formulas for lead to acetate and sodium sulfate. And here we are. PbC2H3O2, that's the acetate ion right there. Okay. And that is, aqueous, so we put an AQ. And then sodium sulfate, Na2SO4, also aqueous, and so we put that there. On the left-hand side is the reactants. Okay, and now we've got to, again, realize we're starting with two compounds here, so it's going to be a double replacement kind of reaction where they're going to switch partners. Lead is going to drop acetate and go hook up with sulfate. Sodium's going to drop sulfate and hook up with acetate. So here's our potential products: lead sulfate and sodium acetate. So again, we have to look at our solubility chart. Sulfates are generally soluble except if they're hooked up with lead. Okay, so this guy is going to be solid. So we are going to have a solid in this reaction. Now let's take a look if we're going to have two solids. Sodium acetate, okay, is part of this alkali metals, and so they are always going to be soluble. And so this guy is going to be AQ. All right, so what we have to do here then for our products is show them. We hook them up. We make sure we crisscross the charges, okay? And then we have to write the S for solid and the AQ for aqueous. So this one is going to be our precipitate, and this one is going to stay in solution. All right, so that's how it's that's how it looks when there's actually a precipitation reaction going on, and you see if we were to mix these two liquids together, we would see some kind of cloudiness form. All right, so here's a couple you try it. So what I want you guys to do is pause the video. Okay, so pause the video for a couple minutes, talk about these in your groups, see if you can figure out, and then restart the video, and I'll go through the explanations of, if it's a reaction or no reaction, and you can see if you did it right. So go ahead and pause the video and talk about these two with your partners. All right, so I'm back. Here we go. Sodium nitrate and calcium sulfide. Okay, these are both aqueous solutions to start with, and we have to figure out if they're going to have a chemical reaction take place or not. So we start out with two compounds. That means they're going to switch partners. Na is going to go with S, and calcium is going to drop S and go with NO3. So what we do first is we write down the chemical formulas of the potential reactants. So we're going to have NaS, right, and CaNO3. All right, and remember we have to crisscross charges. So Na's got a positive 1, S has a -2, so it's actually Na2S. And calcium has a positive 2. NO3 has a -1, so it should be CaNO3 with a 2 on the outside of the parentheses. All right, so we got to take a look and see if either of these guys is insoluble. All right, so sodium sulfide. All right, let's see. Sulfides, check it out. Sulfides are here. They are generally insoluble, except when they're hooked up with our alkali metals. So Na is an alkali metal, so this guy is going to be aqueous. Okay. In fact, sodium is up here as well, so he's soluble. Okay, so Na2S is going to be soluble. It's not going to do, any fun for us. Let's take a look at calcium nitrate. Nitrates are here, okay, and they are always soluble. They don't have any exceptions. So this guy, again, is going to be AQ. Okay, so that's not any fun either. Because if they're both AQ, then no reaction takes place because they're just going to be floating around as ions, and we can't see those guys. So we have to write NR, or no reaction. Okay. All right, let's take a look at the second one, magnesium sulfate, hooking up with calcium sulfide. So let's take a look. First, these are two compounds, and so we're going to rearrange their partners. Magnesium is going to go with sulfur, and calcium is going to drop sulfur and go with sulfate. All right, and so our potential products are MgS, positive 2, negative 2, so that's perfect, and CaSO4, again, positive 2, negative 2, so we don't need to crisscross. All right, let's take a look. MgS. Sulfides are going to be insoluble, okay, unless they're with the alkali metals. Well, magnesium is an alkali earth metal, so that means that this guy is going to be a solid, okay, because those sulfides are usually insoluble. Now, calcium sulfate, okay, sulfates are usually soluble, meaning they're able to dissolve in water. They do have some exceptions, and calcium is one of them as well. So this guy is also going to be solid. Okay, so we're going to end up with MgS and CaSO4. Bam. All right, there you go. Let's keep on moving.